Section 16.8. We have finally come to the final section of the course. The divergence theorem and a unified theory. So what's going to go on in this section is that, well, in section 16.7 we learned about Stokes' theorem. And Stokes' theorem was, in some sense, a generalization to 3 dimensions of one of the forms of Green's theorem, the circulation curl version. But remember, there are actually 2 different versions of Green's theorem. We also had the flux divergence version of Green's theorem, which is, you can see that right here. And so what the flux divergence version of Green's theorem is saying is that the flux over some curve, so a flux over some closed curve C, is equal to the double integral of the divergence over the region, the 2D region that is enclosed there. And so what we're going to do in this section is that we're going to come up with a 3D analog of this. So here is some 3D region here, and we're going to equate the flux over the surface is going to, in some sense, equal the divergence over the region inside. Now, obviously, there needs to be some integral lines slapped onto this. We have to make this precise, but it's going to follow this same basic pattern right here. Now, before we do anything else, we need to talk about divergence. So, here's going to be our definition of divergence. So let's remind you, in section 16.5, divergence of a vector field in 2 variables was partial and partial x plus partial and partial y. Now we're kicking up to 3 dimensions in exactly the natural way that if our vector field f is mi hat plus nj hat plus pk hat, where we're assuming m and mp all are functions that depend on x, y, and z potentially, then the divergence of our vector field f, which we can write either as divf or the del operator dot f, is equal to, you take the partial derivative of the first slot, the partial derivative of the second slot, the partial derivative of the third slot, and you add them up. And let me point out, very importantly, this is a scalar quantity. So a common mistake is to write the divergence as a vector that has this, then this, then this. No, you don't do that. This is a scalar quantity. You add things up. And one way we can kind of see that is suggestive. This dot product here suggests that, well, we know dot product of vectors is a scalar object, so that's very suggestive here. Okay, so this is the divergence here. Maybe we can just do one quick example with this. So calculate the divergence of this vector field. How do we do that? Well, we take the partial derivative of the first function here and with respect to x. And so that's going to be natural log of y. The partial derivative of this function here, y log z, with respect to y, is log z. The partial derivative of this function here with respect to z is x over z. And then we add up the 3 partial derivatives together. And so this is how we calculate the divergence, and we'll be using this in future videos.